All right, so for our fundamentals of DBMS class, we chose airline dataset for our final project. The members involved on our project are Naga, Sandeep, Jaipal, Mukesh, and myself, Jay. I'm going to give a brief overview of the project itself. So we chose the airline dataset from the U.S. Department of Transportation for this case study. Using the data, we have drawn logical and educated inferences for deriving pertinent data using the DBMS concept. The tools we used were MySQL database and a ERD diagram tool, which is called eDrawMax. And below is our reference for where we got the data set. For our data set, we chose a single huge table data set that portrays information about the flights, carriers, airports, delays, and the timelines of domestic flights. This was from the year 2008. We have conceptualized sample case studies on the basis of available data set. Several key columns were added to the existing data set to remove inconsistencies. Through manual analysis and thereupon adding missing data, the noise caused due to the missing data in this dataset has been minimized. Now I'm going to pass off to Sandeep to explain the ER diagram that we created.
Based on the complex airline data set that we have derived 7 entities. And on the basis of these 7 entities, we have come up with the entity relationship model. And here we have the ER diagram in front of us, which shows the relationship between the different entities. The different entities that we have here are the airport, route, flight, calendar, aeroplane, manufacturer, and the carrier. Coming to the relationships between the entities, the entity set of airport and route has got 2 one-to-many relationships in the form of origin and destination. Coming to the next entity set, which is the route and flight, it has a one-to-many relationship in between them. As in, every route has multiple flights running in it, and every flight runs in a single route. The next entity set that we have is the flight and calendar, which is a many-to-one relationship. The flight aeroplane entity set has got a many-to-one relationship. Coming to the aeroplane manufacturer entity set, it has a many-to-one relationship, as in many aeroplanes are manufactured by a single manufacturer, and every manufacturer has multiple aeroplanes. Coming to the last entity set, we have the carrier and the aeroplane set, and the relationship is many-to-one. And next we have Naga, who is going to describe about normalization.
We have achieved the normalization by removing the partial and transitive dependencies from all the relations, and these are the final relations that we have derived, that is the carrier, aeroplane, manufacturer, airport, flight, route, and calendar. These are the final tables that we have achieved. Okay, we went on to normalize the tables and to reduce the redundancies from the data set and to improve the efficiency and data integrity and scalability. The initial data set contained of 64 columns, and from that we have made flight date, unique carrier ID, airline ID, tail number, and flight number as our composite primary key. Okay, in the data set there were certain partial and transitive dependencies. We can see here the partial dependencies and the transitive dependencies. The partial dependencies were the year, quarter, month, day of month, and day of week were derived from the flight date, and unique carrier ID, model ID were derived from the tail number. And coming up to the transitive dependencies, the carrier ID, airline ID, and model number derived from the unique carrier ID and the model ID. And also these are all the IDs that are fully dependent. They are fully dependent IDs. And then we have couple more partial and transitive dependencies. That is the airport sequence ID and market ID are derived from the airport ID. And then we have state name and state flip derived from the airport ID. And also we have created a table calendar by removing the partial dependency, and the date is the unique key here for this table. We have tail number as the primary key for the aeroplane table, and then we have unique carrier ID as the primary key for the carrier table, and then we have the model ID as the primary key for the manufacturer table. And all of this we have removed the partial and transitive dependencies. And then for the airport table we have removed partial dependencies, and airport ID and airport ID is actually the primary key, and then the airport details are stored into an airport table where it is referred to a route table origin and destination airport ID details. And finally, we have normalized all of them to bring it up to third normalized form, and we have created the tables. Jaipal is going to explain the query scenarios next.
Hi, I'm Jaipal.
And I'm Mukesh, and we are going to discuss query scenarios for a product.
In the first query, we are going to find out the occupancy rate, occupancy ratio at airlines in every route. For this, we have joined flight, aeroplane, manufacturer, and carrier tables, wherein we got route ID from flight table and carrier name from carrier table. Now we are adding number of passengers in the flight table for United carriers and dividing it by capacity of that particular flight. And we are rounding it to 2 decimal points. And we have used group by function for route and carrier name.
In the second query, we are trying to find new routes in which United Airlines can operate. In the query, going to the query, here we have got the route ID and the route distance from the route table, and we also got the origin airport and the destination airport of that particular route from the route table itself. And for that, we have to check what all planes the United Airlines carrier can operate in that particular route. And next, we also checked if that particular route is already existed in the United Airlines operation. In our next query, we are trying to find the fastest flight in a given route. And this is the query. In the select statement, we are getting the unique carrier name and the maximum speed of that particular flight and what is the flight number. And in the first block of query, we are trying to group everything by carrier name, maximum speed, and flight number, so that we can get the maximum speed of each flight operated by that particular carrier in the given route. And over here, we are trying to find the fastest flight in that particular route, and we are comparing if the carrier's maximum speed is equal to the fastest speed. By doing this query, we got the below result.
Next query, we are going to display clients of each manufacturer and number of flights bought by them. Here we are using 3 tables, carrier, aeroplane and manufacturer, and joining them, and we are grouping them by carrier name and manufacturer. So we are doing a count operation on tail number which is unique for each aeroplane, and we are getting the results. In our next query, we are going to calculate average time for traveling between 2 airports. To get these results, we are using anonymous block. We started the anonymous block and we have declared a cursor where we are getting difference between arrival time and departure time to the cursor and saving it. We are given airport codes here in the select statement, and now we are opening the cursor and we are putting the value in cursor to hours variable, which is a global variable declared here. And if the difference between time is in positive, then we are just adding it to the total hours. If the flights have landed on the next day, then the difference between the time is in negative, so we are adding 1440, which is 24 hours into 60 minutes. And we are getting total number of flights into one variable, like how many operations we have done. And now we are dividing the total with the number of flights and getting the average. Displaying it in console, which is 15.6 minutes.
Scenario, we want to help United Airlines with sufficient data so that they can analyze delays and maintenance costs of 2008 and proceed to 2009. And the delays involved in an airline scenario are aircraft delays, airport delays, and weather delays. And now here we will see how we are going to calculate the airport delays. And here we are selecting the data from airport table, route table, flight table, and aeroplane and carrier tables. In this, we are giving the where condition where we are filtering it out with United Airlines, so that we will get the data of all the airports reached by United Airlines. Looking at the result scenario, we can say that Cleveland has highest average delays and Detroit with 20.50. So that depending on these delays, carrier can take the delays and they can schedule the flights accordingly. And weather delays. And in this weather delays, we are trying to provide the average weather delays in a particular route for each and every month, so that the carrier can plan their schedule according to the weather delays. And in this, we are using max, min, and average functions to predict the maximum, minimum, and average delays. And we are getting the data from route table and flight table and calendar table and aeroplane tables. And we are grouping it according to date, month, and route ID. And next, going on to aircraft delays. Aircraft delays might occur due to high maintenance of aircrafts. Now, for United Airlines, we are trying to find what are the models that are causing more delays.
Depending on the delays cost, carrier can go ahead with the decision to replace the aircraft or change the model of the aircraft which they are using. And now here, late aircraft delay and carrier delay are the two possible delays which can occur because of aircraft maintenance. By combining the flight table and the aeroplane table, we are able to come up with the average delay of a particular aircraft model. Depending on this, he can take a decision to replace ERJ195 so that to decrease the delays and maintenance.